on Aspera. Yeah, okay. So filling you guys in on Aspera. And again, Aspera is a SmallSat mission funded in the NASA Astrophysics Pioneers Program to study the warm, hot CGM or circumgalactic medium. But what does that all mean? And I'll get to that in a moment. So first, I'd like to take just a moment to give a brief announcement about something totally different. So I'm spearheading a survey on poverty to study poverty rates and poverty inclusion, inclusion of people from backgrounds of poverty in the field of astronomy at all levels. So I'm doing this in partnership with the AAS, the American Astronomical Society, and the National Committee for the Status of Minorities in Astronomy, which is one of the AAS committees. So if this survey is meant to target everyone, not just people from poverty. So if anyone here who has interacted with the field of astronomy, been an astronomer through undergrad, through the professional level, if you'd like to participate, your participation is encouraged in this survey. It's just a totally voluntary, about 15-minute long survey. We got IRB approval for it in February, and you should be getting announcements from the AAS Digest about it in the next couple of weeks. So it's not quite live yet, but it should be live in the next probably about 2 or 3 weeks. So if you're interested and need more information, please reach out to me directly. I'm happy to help. Okay, so let's talk about Aspera and the CGM. So I mentioned this great acronym CGM. So what does that mean? So circumgalactic medium. So every time you took your favorite optical telescope out of your backyard or went to an observatory, again, optical telescope, and observed any old nearby galaxy that you could resolve with your eye, with that telescope. When you look at it, you would only see the inner about 15 kiloparsecs or so, the so-called star-forming disk. So this is where all the stars live, gas, dust, the whole 9 yards there. However, as you could tell from this artist rendition image that I'll motivate a little bit further later on, this is actually a tiny part of the picture of what's actually going on in galaxies to maintain their internal homeostasis. So galaxies are actually undergoing this beautiful cosmic dance, balancing outflow of gas with inflow of pristine and recycled gas. So just to summarize what this means, in the star-forming disks of galaxies, you have high-energy processes that impart mechanical energy into the interstellar medium. These are things like supernova, stellar winds from O and B type stars, massive stars, and even active galactic nuclei associated with supermassive black holes at the centers of galaxies. So these are all great at imparting mechanical energy into the ISM, ejecting gas out of the interstellar medium and into this so-called circumgalactic medium that surrounds these galaxies. So sometimes that gas is ejected and recycled back down, so it falls back down in this so-called galactic fountain mechanism, aptly named. Other times this gas is just completely ejected and outflows. And all the while it has to interact with the diffuse layer of gas that's already there. It sometimes shock heats to extremely high temperatures, as we'll see shortly in a phase diagram. So long story short, though, if we are ever to have any hope of understanding the way galaxies evolve over time, understanding the matter from which future generations of stars and planets will form, we must understand the complexities of this multi-phase gas cycling process. Okay, so what do we know about the circumgalactic medium and their halos, so to speak? So we know that galaxies and their halos are cool. Well, by cool, I mean cold. So in the cold phase of cold molecular gas, we can look at a nearby galaxy, a starburst galaxy called M82, whose star-forming disk is oriented along the green line, kind of diagonally shown on the left-hand side of this image. And the teal, kind of bluish teal contours here are carbon monoxide emission from the J1 to 0 transition in carbon monoxide, the molecule, which is a great tracer of molecular gas. So as you can see, there's lots of molecular gas there, even some gas extending outside of the disk by a large vertical distance into the inner CGM or inner halo of that galaxy. We also see lots and lots of evidence for cooler atomic gas, so slightly warmer than the molecular gas. Now this is traced by the very famous H1 21 centimeter line, this hyperfine spin flip transition in the neutral hydrogen atom, that you can see here in the gray scale, or excuse me, the blue shading scale, and the black contours is that H1 gas, that neutral hydrogen atomic gas. And again, we see evidence for huge filaments extending, tens of kiloparsecs or so from the star-forming disks of nearby galaxies. So this is just one other galaxy, NGC 891, but this is somewhat ubiquitously seen for nearby star-forming galaxies. Okay, we also know that they're warm and dusty. So this is, again, M82 in a slightly more visually pleasing image, at least. The red sort of conical outflow that can be seen in this red scale here is H alpha emission, tracing warm ionized gas, about 10 to the 4 Kelvin or so. We also see dust in the dust blocking the stellar continuum light here in the foreground. And of course, optical showing that stellar continuum from M82 in the star-forming disk itself. Finally, we know that galaxies are very hot and their CGMs are very hot. So again, this is also M82, oriented slightly differently though. And the yellowish cotton ball-like diffuse structure that you could see outside of the star-forming disk here is hot X-ray continuum emission that traces gas that's hotter than 10 to the 6 Kelvin here in that case. So if you've been following along on the bottom portion of the screen, you'll notice I've been tracking a temperature continuum from cold molecular gas all the way up to hot gas, but there's this intermediate warm-hot phase between warm ionized and hot that would correspond to a few times 10 to the 5 Kelvin or so. So that was missing from my previous discussion. So are galaxies warm, hot in this intermediate phase? So if we look at simulations of galaxies, the answer is resoundingly yes. So here's a galaxy's simulated CGM in a phase diagram. So that meaning we have a temperature, a plot of log temperature on the y-axis here and log density on the x-axis. And as you can see, if you follow here to a few times 10 to the 5 Kelvin, the grayscale in the background here shows mass of that simulated galaxy's circumgalactic medium. So tons and tons of gas in that intermediate warm-hot phase. So now if I bring your attention to the colorful squares or rectangles here, those show different metal line transitions that are sensitive to different regions of this phase diagram. So we can use these line transitions in these different atoms to understand the content and behavior observationally of these different regions of the phase diagram. So if we want to study this warm-hot phase, again, a few times 10 to the 5 Kelvin, where all of this tons of masses we have a sort of limited number of options here. So we can look at this neon 6 line from 5 times ionized neon, or oxygen 6 from 5 times ionized oxygen. This neon 6 line is extremely challenging and faint to observe, even harder to observe than the O6 line. So for our purposes moving forward, O6 is the lower hanging fruit. By no means is it easy, and I'll get to that. But I'm going to use that somewhat interchangeably from here on out as a tracer of the warm-hot circumgalactic medium phase. So again, O6 meaning warm-hot gas. Okay, so that was a simulated galaxy. But what do we know about warm-hot gas in the circumgalactic medium empirically from observation? So the vast majority of what we know about this phase of gas in the CGM, especially of nearby galaxies that aren't redshifted, comes from a technique called absorption line studies. So typically quasar absorption line studies. So the basic idea here is you point a telescope typically, but not always, the Hubble Space Telescope at a at a galaxy whose CGM you're interested in studying, and you're just so happen to be lucky enough that there's a quasar in the background of that galaxy, not associated with the foreground galaxy that you're interested in. And the quasar spectrum is somewhat well characterized and known from quasar studies on their own. And so you can follow basically the path of light in the line of sight from the quasar. It gets absorbed by certain elements that exist within the circumgalactic medium of the foreground galaxy. And you can see those components of the CGM in the foreground galaxy in absorption line features in the spectrum that you would measure from your telescope. That's a combination of the quasar and the absorption features. So this is an extremely powerful technique, again, that has told us most of what we know, if not really very close to all of what we know empirically about warm, hot circumgalactic media and galaxies. So what have these studies shown? Typically, again, it verifies there's tons and tons of mass in this O6 phase, this warm, hot gas phase. More mass than the sum of all the stars in these galaxies typically. So it is a dynamically important component. And it takes a lot of energy to sustain there. So it would take about 10% or more of the galactic feedback energy budget just to support this amount of gas in the CGM. Now, if you've been following along, though, no matter, these are very important, but there are a few caveats to studies like this. Namely, you have to be lucky enough to have a background quasar in the background of the galaxy you're interested in studying. And if you don't, then you're out of luck. And also, even if you do have that quasar, you only have information along these pencil beam single lines of sight. So it is by definition impossible to study volume-filled two-dimensional structures in galaxies through this method. So if we ever want to study the full volume-filled structure of the CGM, we need to move to emission line studies that can be sensitive to the whole of the galaxy CGM rather than just single sight lines. Okay, so what do we know in emission, though, from of this O6 line? Again, in nearby galaxies. So drum roll, please. What we know is we have 4 detections in 4 sight lines in 2 galaxies. That's it. So the latest on this is a paper that my colleague Han Chung wrote with myself and another colleague, Erica Hamden at University of Arizona a couple of years back, where we looked at archival FUVE data, FUVE being the Far UV Spectroscopic Explorer, which was a UV spectrograph, space spectrograph that launched, I think, early 2000s, late 90s, something like that. So we looked in the archival data with a new updated pipeline to search for new O6 emission detections. The previous detections, there was only 2 from an Odd-et-al study in 2003, originally detected O6 in regions A and B on the left-hand side here in NGC 4631, but did not detect any O6 in NGC 891 shown on the right-hand side in 3 fields. So with our revised pipeline, we found 4 completely new detections in fields I, F, and H in NGC 4631, and in field number 2 in NGC 891. That's the state of the art here in terms of emission detections. It's been an extreme challenge to get access to O6 emission for a number of reasons that I'll discuss shortly. Okay, so there is a need for us to map this volume-filled warm-hot component to the so-called coronal gas or circumgalactic gas. So I'm certainly far from the first person to ever posit this. Way back in the 70s, famous astronomer Lyman Spitzer said, while the hot gas observed with Copernicus is very similar to the extended corona suggested nearly 20 years ago, the origin and spatial distribution of the observed coronal gas is not at all certain. So that was quite a while ago. So why have we still yet to do this? Well, the answer is likely threefold. One, this O6 line, in the rest frame at least, if we don't want to study redshifted emission, this line occurs in the far ultraviolet. It's very faint, and there may be a filamentary component to this that has been biasing results to date. Okay, so let's take it one by one there. So it's in the far UV. So the strongest line, that O6 line, it's actually a doublet occurring at 1032 or 1038 angstroms in the rest frame, 103.2 and 103.8 nanometers in the rest frame. So immediately, shout out to the ozone layer and the atmosphere for keeping us all alive, but immediately you're not going to be able to observe any of that from the ground. You have to go to space and get above the bulk of the atmosphere to have any chance at observing that radiation. The surface brightness of this line, this doublet, is certainly less than about 1 × 10⁻18 ergs per second per square centimeter per square arc second near redshift 0. If you're not familiar with these weird astronomy CGS surface brightness units, this is a pretty absurdly low number, so it's extremely faint. And lastly, this one's a bit more subtle. So there may be an element of luck biasing some results. So what do I mean by that? So on the upper left-hand side of this image here, I'm showing a simulated galaxy's oxygen-6 emitting gas morphology, again, from simulation. And as you can see, there's tons of discrete features like filaments extending away from this horizontally oriented stellar disk here. There's even bubble-like structures that would be consistent with super bubbles from supernova regions, H2 regions within disks ejecting gas out of them, et cetera, et cetera. So again, lots of discrete structures. So it may be possible that previous studies with FUVs, which observed only a handful of small fields, like the ones on the lower left here for 4631 and lower right for NGC 891, could have just gotten unlucky. So in 891, maybe they pointed at fields more similar to region beta in the simulation. And maybe in 4631, they pointed at fields more similar to alpha in the simulation. We just don't know. We need a volume field mapping campaign to understand the morphology better to get any information out of that. Okay, so adding fuel to the fire, far UV optics and detectors are historically extremely inefficient at these wavelengths, and it's very hard to get a payload into space. Until now. So there have been some pretty huge leaps and bounds in the last 10, 15 years or so that have made a study similar to Aspera possible for the very first time. So namely, starting in the upper left here, ultraviolet coatings. So optics are very bad at reflecting UV photons on their own. So we need to coat them with special coatings to enhance the reflectivity. I'll get into a little bit more about that later. But Manuel Quijada and his lab at NASA Goddard Space Flight Center have been developing these coatings and have brought the reflectivity of these optics up to nearly 80% or so, which is huge in the far UV. Lower left here, we have EM-CCDs, electron multiplying CCDs, again, for far UV applications, done typically through a delta doping process and anti-reflective coatings applied to these CCDs. So Sholay Niczad at NASA JPL and my colleague at Arizona, Erica Hamden, are really pioneers in this field. And then microchannel plate detectors, a different flavor of detectors. So these have been historically widely used in the far UV, more so than the EM-CCDs. But the key point being here, they're getting smaller and smaller for use on small platforms. And then on the upper right here, more in the news, you may be familiar with SpaceX and the recent successes of the Falcon 9 and the NASA SmallSat rideshare program, which has drastically reduced the cost of sending small science payloads to space. So in this new environment that I've been referring to as the Wild West of UV space astrophysics, Aspera was born, my little mini fridge in the sky. So Aspera, again, is funded in the NASA Astrophysics Pioneers Program. We're one of the inaugural selected missions in that program in 2021. And here's a quick snapshot of our team, the Aspera team. So again, I'm Carlos, I'm the PI here, along with Erica Hamden, the deputy PI, and Han Chung, the project scientist. I'm not going to go through everyone's names here, but a few key partners, Ascending Node Technologies, is a local Tucson company that we contract with to work on orbital mechanics and concept of operations development, as well as flight software development. A little bit of a jack of all trades company there. Sensor Sciences LLC is building our detector system. We use microchannel plates, a little bit more on that later. University of Toronto Institute for Aerospace Studies Spaceflight Labs, or SFL, is building our spacecraft. They're our spacecraft partner, Simon Grocott leading that. And we have a slew of external science team, co-Is and collaborators from Space Telescope to NMSU, New Mexico State University, even collaborators in Germany at Ruhr University in Bochum, just to name a few. So you may notice a color scheme here. So the blue colored names are early career faculty and postdocs. The orange colored names are graduate students. The yellow names are undergraduate students. And the purple names are early career engineers and technical staff. So I'm happy to report we are just about at, or I have to double check, but I think we're at the 50% early career participation threshold for this project, which I'm very proud to say. Okay, so what are we aiming to do with Aspera? So let's take a quick look at the science objectives. So the overarching goal is basically to address the 2010 decadal New Worlds, New Horizons question: how do baryons cycle in and out of galaxies, and what do they do while they are there? Very similar question to the 2020 decadal that has since been revised. So in order to address this big question, which we of course will not be able to fully answer and flesh out an answer to ourselves, but we have three directly actionable objectives that'll help us understand that goal a little bit better. So one, we want to determine the ubiquity of warm hot gas. So we'll do that by observing a sample of nearby galaxies in extremely deep exposures to detect that O6 emission in a systematic way, in order, again, to understand how often we see O6 emission at certain levels in typical star-forming galaxies in the nearby universe. Science objective 2 is to study the morphology. So this is the mapping campaign to study the two-dimensional morphology, the volume-filled morphology of O6 emitting gas. So if you look at the figures here in the upper left, is that simulation we looked at before, developed by Lauren Corleys and Shimonovich 2016 for that study. And on the right-hand side is a mock observation of what we'll be able to observe with Aspera, given our instrument parameters and pointing knowledge, stability, jitter, all of that factored in as well. Science objective 3, finally, is to see what it all means for galaxy evolution. So we'll be measuring line profiles and kinematics of that O6 emitting gas into the line of sight to then cross-check that with galaxy evolution models and gas flow simulations to see the implications for that gas. A few words about our science targets. So we have 21 targets, of which we'll observe a subset of 10. I'll talk more about the baseline mission, though, in just a moment as well. They are all edge-on targets. You could see a snapshot of just 6 of them as a sample shown on the right-hand side here. You'll notice they are all oriented to be edge-on or close to edge-on. Simple explanation for this here is observing a galaxy edge-on allows us to immediately and very easily distinguish O6 gas that would be in the interstellar medium versus in the circumgalactic medium. So we'll know immediately if it is vertically displaced from the interstellar medium. So we don't have to play any projection games and factor in factors of Sinai and things like that. On the left-hand side here, I'm showing where the orientation of our targets on the sky, along with the galactic plane and ecliptic here in the dotted lines. As you can see, we have a lot of targets in the northern hemisphere. This is a bit of a selection bias. Just historically, the most well-studied nearby galaxies, of course, are in the northern hemisphere for historical reasons. But we do have some southern hemisphere targets here, and it behooves us to have a wide distribution of galaxy targets on the sky, so our observing efficiency is high. In other words, we'll be able to bounce back and forth between targets based on availability and launch date without kind of hamstringing ourselves into a certain subset of targets certain times of the year. Uh, so a bit of an eye chart here. Sorry about that, but just for completeness, if people are interested, here's the full list of our 21 targets. Again, in case anyone's interested. Selection criteria shown on the left, but just to walk through a couple of these to better understand the motivation here. Again, all inclination higher than 78 degrees. This is another way of saying edge on or close to edge on. And perhaps the most controversial selection criteria is our extinction. So we choose galaxies with an extinction less than 1 magnitude at the 0.6 line, meaning the 0.6 emission would be attenuated by a factor of about 1 magnitude or less. Now, this is a rather large number of extinction, a large amount of extinction at the 0.6 line. However, we do have that brand new NGC 891 detection from the FUV study that I referenced a little bit earlier. And we're very excited to see that because NGC 891 is a very notoriously dusty galaxy with lots of dust attenuation and extinction. And so if we were able to detect 0.6 with FUVs, relatively older instrument, let's say, with that high extinction, then we're pretty confident we'll be able to see it for galaxies that are much less than 1 magnitude. So we keep that cut at 1, but to make us all feel better, at least 10 of our targets have extinctions much less than that, less than 0.35 magnitudes. Also, these are very studied galaxies at other wavelengths as well. So we made sure other ancillary data exists so we can tie what we find in 0.6 back to other phases of the CGM. Okay, so let's define the baseline mission and the threshold mission. So the baseline mission is effectively what we are setting out to do. What do we do? What are we planning to do? What science are we planning to deliver? So we plan to observe, again, at least 10 nearby galaxy targets in single deep fields to study the ubiquity of 0.6 emission, produce at least 3 0.6 emission maps with a minimum amount of spatial coverage in the innermost 10 arc minutes from the galaxy center, with final spatial resolution less than 120 arc seconds, with a spectral resolution of about 1500 and a surface brightness depth of 5 times 10 to the minus 19 ergs per second per square centimeter per square arc second. These would be the deepest far UV observations in history. Now contrast that with our threshold mission. So the threshold mission, a good way to think of this is the minimum amount of mission, that NASA would fund, so to speak. So the threshold mission would only come into play in case of some kind of catastrophe or an accident or something goes wrong with the mission. So in that case, we would observe at least 3 nearby galaxies in single deep fields and produce at least 1 map for a nearby galaxy with a final spatial resolution less than 600 arc seconds. This is the minimum to distinguish disk from halo. Spectral resolution about 173. This is to resolve, cut off a little text there, but to resolve the 0.6 line with nearby geocoronal lines from the atmosphere, from Earth's atmosphere, down to a surface brightness depth of about 4 times 10 to the minus 18, which is what we detected in that FUV study with NGC 4631. Now, the threshold mission is extremely resilient. As you could tell, this is kind of a very, very worst case scenario. So the threshold mission is achievable in 6 months of science operations, even in the worst case system performance. And this worst case performance corresponds to a catastrophic contamination event of our optics that reduces our throughput by 50%, a very bad situation. And in addition to that, us losing an entire channel of the spectrograph. So you'll see in a slide or two, Aspera is comprised of 2 identical redundant channels to effectively double our instantaneous exposure time. So even if we lose a whole channel and have a 50% throughput loss of that single channel due to contamination, we still deliver the threshold mission in 6 months. Okay, a little bit about data flow and the data reduction pipeline and archiving. So I want to point out a incredible postdoc working in our group, Dr. Miriam Kepler. She's leading our pipeline development. So effectively, we identify our level 0 through level 3 data products, all of which we will be archiving with our archive partner, MAST. And so effectively these level 0 products will range from time-tagged event lists. We'll be doing processing and documenting the processing on the archive as well. Perform calibrations at level 2, spectral extraction, flux calibration, all the way down to our final data products of image cube reconstruction for each of our target galaxies. Image reconstruction is a bit of a can of worms. It's currently under development, but since we will have irregularities and scatter data onto we won't be able to observe onto a nice, perfectly oriented square grid. So in order to account for that, we have to write an algorithm that takes those irregularities into account. I don't want to go into a ton of detail here, but the algorithm we're writing here is based closely on the manga image reconstruction methodology. So please, I'd like to point people to the Law et al. 2016 manga paper for more detail on that. And we are working on a publication of our own to discuss the Aspera specific image reconstruction algorithm. So what can you expect to see if you're interested in using any of the Aspera data? So it'll all be public a few months after the mission is complete. Our archive partner will be MAST, the Mikulski Archive for Space Telescopes, and we'll be archiving all of the level 0 through level 3 products that you can see here. In the interest of time, I'll skip ahead though. Okay, so getting into the nitty-gritty of the instrument, here's what the latest CAD model of our Aspera payload actually looks like. As you can see here, we have 2 identical channels, as you can see from these entrance apertures here on the left and right-hand side of the payload, that house a baffle assembly to mitigate scattered light within the baffle before it reaches our off-axis parabolic mirror, or OAP mirror. Again, identical on both sides, but the right-hand side here has the cover not shown. It's transparent, the teal cover here. So after the light hits the OAP, it goes through the slit and then hits our gratings. So we have dispersive element gratings here. I hope you could see my cursor pointing out on the left-hand side of the instrument here. After the light is dispersed, the spectrum is then imaged directly in the focal plane by our microchannel plate detector. So we have one microchannel plate shared between the 2 identical channels. Again, cost-saving measure in the Pioneers program there. The whole spectrograph sits on top of the electronics bay, single star tracker unit, and we interface directly with the spacecraft with through this base plate at the bottom of the instrument itself. The design of this, if you're interested, is inspired by that FUVE telescope. It's a mini FUVE cut in half, so to speak. There, it's a Roland circle-like spectrograph. Again, 2 of them. Wavelength coverage of 101 to 106 nanometers, R of about 2300, spectral resolution, that is, spatial resolution about 78 arc seconds from this. And field of view, our slit field of view will be 60 arc minutes long by 30 arc seconds wide per channel. The instrument will be about 2,000 times more sensitive than the Hubble Space Telescope Cosmic Origins spectrograph instrument. Again, this is only in that 101 to 106 nanometer bandpass area. So this is not to trash COS in any way. We are a lemon zester, whereas COS and FUVE, for that matter, we're Swiss Army knives, so to speak there. But it is a testament to what could be done, even with a teeny tiny instrument like this one. Banana for scale, so you could see roughly how large the instrument actually is. This is a 3D printed model of the payload, but at 1-to-1 scale. So this is exactly as large as it will be. And here's one of our great graduate students, Afaq Khan, attempting to steal that 3D printed model at one of our NASA reviews. So we give him a hard time for that sometimes. A little bit about our detector system. So our microchannel plates, shown on the left-hand side, this isn't our actual detector. This is Sensor Science's sort of stock photo, I guess. But it is very, very close to our actual flight detector system there, that image. So these are cross delay line, cesium iodide photocathode, optimized MCP detectors, for the far UV. So we have QEs, quantum efficiencies for these detectors, greater than 35% at 103 nanometers. It's a very good number, not quite as good as optical for other CCD systems and things like that. But in the far UV, these are pretty incredible. Spatial resolution less than 35 microns. These are TRL 9 detectors, TRL being technology readiness level. These have flown to other planets, this similar detector system. We have actually our sister detectors are on the JUICE mission to, I think, a moon of Jupiter as we speak. So the footprint of the focal plane is shown on the upper right here. As you can see, we have a shared detector for the two identical channels, and you can see the footprint of the spectra, how it lands on the focal plane itself. So flight optics and coatings. So we need to coat, again, our flight optics to be optimized in reflectivity for the far ultraviolet photons that we want to study. So on the left-hand side here is the project scientist Han Chung performing a fit check of our OAPs, the sort of primary mirror for the instrument, onto our coating fixture. So that's a little copper plate fixture that we mount the mirrors onto, along with four little circular holes for witness samples when we apply the far UV coatings onto the surface. And on the right-hand side are the same OAPs and witness samples fresh out of the coating chamber. Your eye can't see much of a difference, but they are much more reflective to UV photons. So why do we need to coat these things? So on the left-hand side here is a plot showing reflectance versus bare aluminum and aluminum plus lithium fluoride coatings. So really the main point here is the ideal surface for reflecting UV photons would be bare aluminum. However, bare aluminum oxidizes almost immediately in atmosphere. And so it's extremely challenging and just unfeasible to work with bare aluminum. So we apply a bare aluminum layer to the optic, and then immediately at the same time apply a protective layer that is transparent to UV photons on top of it. Typically, that protective layer are things like fluorides, lithium fluoride, magnesium fluoride are the most typical for that. And in the far UV, the most optimized fluoride is that lithium fluoride. So, however, the lithium fluoride itself and all of these fluorides unfortunately also degrade in atmosphere. They are extremely sensitive to contamination from molecular contamination. And as you can imagine, the most prevalent molecule in atmospheres that we are worried about is water. So relative humidity is a large issue for us to control when we're handling these optics. So all of these lines are different conditions, different relative humidities for different coatings, a bit confusing. But in any case, you could see they all go down over time with exposure to humidity. So we have to go to great length to control the humidity in our clean room and make sure that all of our coated optics are stored in a dry nitrogen purge so they are not subject to this molecular contamination. So a series of technical challenges for the mission. Everything is sensitive to contamination. So those optics, the coatings are sensitive to contamination, and the detectors themselves too. They actually have similar fluoride coatings on their photocathodes that will degrade with humidity and other molecular contamination. So the molecules that we're worried about in addition to moisture are silicons. So silicon greases are a major contamination risk for us. So all of our vacuum chambers that we test and calibrate in, we can't use any vacuum greases for them. We need to make sure also our vacuum pumps do not have greases floating around them that can contaminate certain hardware. We also need to align our optics extremely precisely. Our alignment tolerances are at the handful of micron level. So that is a large technical challenge for us to tackle. And we need to coordinate closely with our spacecraft vendor to make sure our spacecraft system is compatible with the mission that we need to do. So first, taking it one by one with those technical challenges, contamination control. So this is kind of the major hurdle for this project. So just a sample of some measures we take to control contamination in our clean room and the clean environment in which we need to build the spectrograph. So on the left-hand side, here's our optics shipping container. So you could see again, 2 OAPs and witness samples just kind of hanging out in this plexiglass shipping container. So we literally created this to be TSA compliant, the clear top. It fits within a nice Pelican case that we can bring onto a plane so that we can hand carry these optics from our coating vendors back to Arizona to be stored and integrated with the instrument. These are actively purgeable, so we can purge these with dry nitrogen, ultra high purity gaseous nitrogen, and backfill this, valve them off, and then bring them onto a plane. On the right-hand side, here's our calibration chamber. So we have a couple of vacuum chambers and a TVAC chamber, a thermal vacuum chamber in the clean room that we need to precision clean with IPA, isopropyl alcohol, and acetone to make sure that they are pristine and free of molecular contaminants within them that can be spun around when we start pumping them down. So this is one of our grad students at FOTCon, and they're cleaning that along with Eli Garcia there. On the left-hand side, here's our dry nitrogen storage boxes. This is just a couple of them. We have a few more too. And you can see the nitrogen tank on the lower portion here. So these are boxes that we can control the flow of dry nitrogen into to make sure that when we store optics and other things inside of these boxes, that they are extremely dry as possible. Right-hand side here is me literally cleaning the floors of the clean room before we commission the clean room to get rid of any gunk that could be on the floor and walls. This was a fun and tedious and long process, but again, precision cleaning of everything. Optical alignment is another interesting technical challenge that we have to deal with. Again, really tight tolerances. So we use a zygo interferometer here, along with a computer-generated hologram system, which you could see on my cursor here sitting on the optical bench there, which basically produces interferometric fringes for us to minimize that is specifically designed for our optical system to be able to align it. So once we're in alignment with the OAP and grading system in the layout that we have for the instrument, we'll minimize those fringes and be in alignment to the sub-micron level. So really interesting technique for this. A lot of detail here that I'm glossing over, but let me know if you're interested and I can hopefully answer some questions if you are. Okay, so I'm running out of time a little bit, but I want to talk a bit about the other things a space telescope needs to do. So we need to transmit and store data. We need SSDs for that, radio transmitters. We need to acquire targets. We need to be able to sit and stare at those targets and point at them and know what we're pointing at. We need to generate power and store that power in batteries and via solar panels. And we need to control the thermal environment extremely precisely so there aren't thermal gradients across the optical bench that can throw the instrument out of focus. And finally, propulsion. We actually don't have any propulsion for Aspera, no delta V needed, thankfully, so that simplifies things, though these are options. So, and also we need the brains. We need a command and data handling chip to be able to regulate all of these processes. So our spacecraft vendor effectively does all of that for us. So I can't talk in a ton of detail because of NDA about the specific technologies and instruments within the spacecraft, but our spacecraft does all that stuff, and it is built by the University of Toronto Spaceflight Labs. This is an actual qualification unit of our full Aspera spacecraft. This is the entrance aperture lid that will pop open during flight. It'll pop open upward to expose our entrance apertures for the spectrograph. And the solar panels are in a stowed position on the side here and on the opposite side that you can't see. And on the right-hand side here is the Aspera team and the SFL team catching a baseball game at the Rogers Center, watching the Blue Jays. As you could tell, we are a pretty low-funded NASA project based on us sitting in the nosebleeds. Oh yeah, and this is an image, a CAD image of what the spacecraft will look like with the solar panels deployed. About the size of a mini fridge, yeah. So you can see it sitting on a sort of normal desktop there. That's roughly about as large as the instrument is, or excuse me, as the spacecraft is. So this is a fun little question. I'm going to glaze over it again because I'm taking up a little bit too much time. But it's just fun to think about. In general, roughly how much do you think it costs to launch an Aspera-sized spacecraft? We're about 60 kilograms in total into low Earth orbit. 30 mil, 3 mil, 300K, or 30K. And interestingly enough, it's about 300K. So again, this is more than an order of magnitude down from what it was about 10 years ago. So again, wild west of space. Future of Aspera. So Aspera will be a part of will be a rideshare payload. This is an actual image from a SpaceX rideshare launch from a Falcon 9. You can see all the Starlink satellites stowed on the bottom portion here, and all these other payloads mounted on these Espa rings. So Aspera will look like one of these, probably near the top on a smaller Espa than these Espa Grandes on the bottom. We'll launch in the fairing on the top portion of a rocket, probably a SpaceX. We don't know yet. It'll open. Now we're in the artist rendition category. Fairing opens, exposes the payloads, and spring releases them from the Espa rings into orbit. Oh, a little bit about programmatic. So again, we're in the NASA Astrophysics Pioneers Program, which gives us a cost cap about 20 million. The schedule is an extremely challenging hurdle. So these are 5 years cradle to grave. So beginning to close out, so 5 years from start, we need to have everything published. We need to have all the data taken, the whole 9 yards. Rideshare and launch details will be known, should say 1 year out from launch. So we are not quite there yet to know that, though we are currently talking with LSP to understand what rideshare options we have. Quick look at schedule and where we are now. So we just passed CDR critical design review with NASA a couple months ago, or last year. Oh, sorry, I thought I updated this figure, but this red dot should be just a little bit further off to the right there. So we are currently in the payload assembly and testing phase, the INT phase. We'll have environmental testing at the end of this year. We'll integrate with the spacecraft early next year with a planned launch date near the end of 2025. Great. So recapping and closing out, the CGM is extremely crucial and important for understanding galaxy evolution. We need to move to a paradigm where we're studying it in emission, and devoted satellites like Aspera can do that. We're an Astrophysics Pioneers mission in the far UV with the goals of mapping 06 emission. And the payload build is happening now with the planned rideshare launch in the end of 2025. Happy to answer any questions. Thanks for your time.
All right, thank you. Any questions to our speaker today? Please go ahead.
Yeah, these Aussie Sigmund microchannel plate detectors, they can experience detector burn-in due to gain sag. Is there anything you're looking at that's bright enough that that's a concern?
Gain sag, yes. So I can't claim that I'm a MCP expert, but after tons of conversations with Ozzy, the gain sag issue over our mission lifetime is not much of a concern for us. So I'm not sure, I may have neglected to mention how long our prime mission is set to be. We're set to have an 8-month-long baseline mission. So in that time, we're not worried about much gain sag at all. If we were going to be up for, a couple of years, it would start to become an issue for us. But apparently these cesium iodide cross delay line detectors are a lot less susceptible to gain sag as well.
Well, it depends what you're looking at. I mean, we have to adjust we have to move where the spectrum goes on our detector, a couple times a year because of burn-in, but we're probably looking at stuff much brighter than you are.
Yeah, that's another thing. So I think Ozzy also mentioned there's, we can get rid of some of that burn-in from flying red LEDs or something like that. But again, we're hoping to look at extremely faint stuff. And even our calibration targets are not that bright. So as long as we don't mess something up and look at the sun, we shouldn't, knock on wood, have too much of that issue.
Okay. Go ahead.
I have a question, but it's more for the science part or the theoretical part. So you said that this warm hot gas is supposed to be in the halo, but it hasn't been yet detected, right?
Well, it has been detected in absorption many times. But in emission, it's only been detected in those four regions that I mentioned in those two galaxies.
Okay. So the amount of warm hot gas is well known in the galaxies. Like, I thought I understood that is not well evaluated, like how much of this gas is in the galaxies.
Right, yeah. So empirically, it's still pretty open of a question. We're relying on those absorption line studies, which are limited in spatial scope. But from what we believe from simulations, in order to simulate gas that's similar to what we observe in other phases, there needs to be this intermediate warm hot phase that's kind of at the peak of the cooling curve, that most of that hot phase gas will cool through to coalesce onto the disk to be accreted onto the galaxy. But you're right in that empirically it's still somewhat of an open question into how much of this gas actually exists en masse in nearby galaxies.
Because well, I wonder, maybe this is a very far-fetched thought, but I wonder how much this gas would count against dark matter in the halo.
I'm sorry, can you repeat that? Count against what?
The dark matter. Because if the amount of gas in the halo is very high, right? Wouldn't that be
Oh, I see. Yeah.
the dark matter that makes like the mass, the material of the star in the halos move at higher velocities?
Oh, that's right. Yeah. So so this ties back to the missing baryons problem, which is kind of a bigger part of a bigger problem in terms of galaxy evolution studies. So there are budgets in each phase of the CGM, and right now there's a theoretical bar basically that has yet to be filled by observation in that warm hot phase. So we're finding all this hot phase gas that can be explained and wouldn't contradict some of the dark matter studies that account for rotation curves in galaxies and the kind of plateauing of rotation curves near the edges of galaxies. So though we might, I mean, unless we find like orders of magnitude more O6 gas than we expect to find, this shouldn't be a contradiction to dark matter theories, especially to explain rotation curves.
Okay, thank you.
Yeah, but if we do find orders of magnitude more, that would be an interesting thing as well.
All right, great. Any other questions? Please go ahead.
You mentioned there's a strict limit to the end of the mission. Are you like guaranteed to hit that limit because of some technical issue with the spacecraft, or is there some possibility that you could do like an extended mission if the spacecraft is still in good health?
Yeah, so that end of the mission there, that even our 8-month primary mission is structured solely based on that's when we run out of funding. So there is a likelihood, assuming the instrument is operational, and at the end of that period, there would be a high likelihood that we'd be able to ask for more funding. So we'll knock on wood for that. But yeah, the lifetime of the mission as of right now is limited solely by funding.
All right, sounds good. Hopefully we don't need to ask for more money.
Yeah, I
Any-
agree with that.
Any more questions from online participants? Okay, I think I have a question. So because of the narrow band, were you only be collecting oxygen-6 line, or are there any other secondary lines too?
Yeah, that's a good question. So, due to the design of the instrument and especially the, spatial constraints of the instrument itself, our performance, spectral performance falls off rather rapidly outside of that 103 or 102 to 106 nanometer range. So we could theoretically be sensitive to some photons outside of that. However, our resolution would be pretty darn low, depending on exactly where. So we may be able to observe like Lyman beta, for example, which is pretty nearby. But however, we'll be definitely drowned out by nearby geocorona emission right around there too. Along with some other oxygen lines in the atmosphere that will be rather bright compared to the other lines we may be interested in studying.
All right, great. Looks like there are no more questions for you. It was great talk. And let's thank our speaker again.
Great, thank you, everybody.
Just if you could hang around, just a quick announcement, I think. Dr. Vargas, are you still there? I think we lost him. So he was interested in meeting his students, if there are any students, like open discussions.
Oh, sorry, I am still here.
So if you could hang around for a couple of seconds, maybe there are students that are available for open discussions, like possibly working with the projects, or if anyone of interested in talking with him. That's what Dr. Vargas was interested to talk to. Like any graduate student, undergraduate students, possibly looking for a school or looking for projects. Maybe we can get some money here, working from here. Well, was that an option? Are there any smaller projects that are assignable?
It's potentially possible, but as of right now, I'm not sure. I don't have any ammunition for that right now, let's say.
Yeah, okay. All right,